This is the second masterclass of Power Electronics Masterclass series. In this masterclass session, we will be talking about the general overview of DC to DC converters. Yousef and I will deliver today's masterclass. To introduce ourselves, I am Hakan. I'm co-president and electronics team advisor of Hyperloop Manchester, and Yousef is one of our great members in electronics team. And Yousef is on the call as well.
Hello, guys.
Hello. So okay. So here's a recap from the slide that has been presented during our last masterclass. You can access our last masterclass on our YouTube channel, and we will provide you a QR code at the end of this masterclass for you to catch up with the previous masterclass. So this masterclass will make much more sense if you watch the previous ones. So DC to DC converter is an electronic circuit that converts a direct current source from a specific voltage level to another voltage level. Simply, it changes the magnitude of the output voltage without changing the type of the current source. It can also be called as a type of electric power converter. Before using the DC to DC power converters in our life, the voltage of a DC supply was converted to a DC voltage in a higher level by first converting it to an AC voltage first, and following that, the resultant AC voltage that we obtained from the first step was input to a step-up transformer and rectifier respectively. So long story short, it was a long process to perform a simple work. Certainly, DC to DC converters make things much more easier in our life. The scope of DC to DC converter use is quite wide, including various applications in our life. They are commonly used in power supplies for home electronics and data centers, control of DC motors, solar power, electric vehicles, and LED lighting. And as a footnote, I want to add that LED power source is a kind of DC to DC converter that regulates the current throughout the LEDs in a design circuit. So this is an important footnote, by the way. So in order to analyze any type of DC to DC converter, there are 5 essential rules that must be considered. The analysis of each type of DC to DC converter will start to be covered in the next masterclass next week, which will be about step down buck DC to DC converter. So for now, I just want to mention the essential rules that we will be using in the next masterclass videos. As a footnote again, we are performing the analysis in periodic steady state conditions, sorry. You can see that PSS stands for periodic steady state, and we will be using the abbreviation of periodic steady state in the further slides. So please bear in mind. So this means that the analysis is performed in a fixed period of time and with identical waveform. Also, we assume that the following rules in circuits also hold in the average domain. This is really important as well. So we are taking the average result of the calculations, because like there are like many variances, and we take the average of them. That's why they can be formulated that simple. So let's start introducing the essentials we need for analysis. The first rule that I'm going to mention is Kirchhoff's current law. As can be seen on the illustration here, this rule simply signifies that the sum of the average current flow is like into one node here is 0. In other words, like I1 plus I2 plus I3 equals IN. It is like too simple, and there is a mathematical formulation for it. And Our second rule is Kirchhoff's voltage law. Again, as can be seen on the illustration, this rule essentially implies that the sum of the average voltages in a mesh, this is a mesh, this is called a mesh, this loop, I mean, in a mesh is 0. So you can see the mathematical formulation here as well. So if we continue on essential rules, our third rule is finding the capacitor current in PSS conditions. In PSS, the initial voltage and ending voltage in a periodic cycle across a capacitor are the same. So this leads that the average current flow into a capacitor is 0. Our fourth rule is finding the inductor voltage in PSS condition again. Similarly, in PSS, the initial current and ending current in a periodic cycle across an inductor are the same. So this shows that the average voltage across an inductor is 0. In addition to all of these 4 rules, there is another helpful rule that can be used in PSS analysis. Consider a power conversion circuit which only uses switches, inductors, and capacitors. As a footnote again, these are the essential components of a power converter circuit. Therefore, we have mentioned the previous 4 rules. These mentioned components are all lossless components, ideally. This means that no power is dissipated in these components, but again, unlike the real life results, is ideally in ideal conditions. Therefore, we come up with the following rule, which is the conservation of the energy. If the circuit is lossless, as mentioned, the total input power should be equal to total power output. So P in input power equals output power, simply. All in all, we have we have now 5 equations in PSS that can be used to find out average voltages and currents in a switching power circuit. We will perform these aforementioned calculations in the next videos of Power Electronics Masterclass series, which will be available in the following weeks. So stay tuned for more details on the DC converter analysis. Now my friend Yousef will take over my place to continue our masterclass, starting with the types of DC to DC converters. Floor is yours, Yousef. Let me make you the co-host, by the way.
Yeah, that would be great. Okay, we go into the types of the DC to DC converters. We have the first type is obviously the type we're discussing, is the step down DC to DC converter, which is the buck DC to DC converter. And what does that mean? It means like the voltage input, the DC voltage input is going to get smaller, which means the voltage output is going to be less than the voltage input. And there's many applications for this buck DC to DC converters, especially in small scale electronics. The step-up DC to DC converters, which is called the boost converter, you give it a V input, voltage input DC, and you get a larger voltage output. This helps us a lot in boosting the voltage when needed for feeding DC motors that needs larger voltage than the battery. So we feed the step up to DC to DC converter to the battery, and we boost the battery voltage output to feed it to the, say, DC motor. And we have now the step down, step up DC to DC converter, which is called the buck boost, which this converter usually changes the polarity of the output. The output is changed. It can make it step up, it can be step down, but the most important part that it changes the polarity of the voltage. And we have the SEPI DC to DC converter, which is not going to be covered. The main part of the say converters, as Hakan said, switches, inductors, resistance, and capacitors, which are the main component, electronic components. And the canonical cell makes it easier for us to visualize and analyze the actual circuit. And as you can see, each node represents a common, an input, and an output for each type of the buck boost converters. As you can see in the next slide. This is the buck step down DC converter, where the switch is at the current, the source current, and the diode is parallel. And this is the common point. This is the output. The output is at the inductor, at the end of the inductor, and this is the input point. While in the boost step up, the switch, the inductor is at the source point, and this is the common point, common node, and the switch is parallel, and the output is at the diode, the voltage output, because we're talking about voltage, which are parallel. The voltage at the R as the same as the VC. As you can see here, the relationship, you can say transfer function of this circuit is V output over VS, which means that the voltage output is going to be less than voltage S than the source voltage, because you know the D is representing the diode, and diode are usually less than 1. The voltage across the diode is always less than 1, which it's usually 0.7, I guess, but it depends on the diode. So it's always going to be less. The voltage output is going to be less than the voltage source. While in the buck boost, opposite polarity, there's opposite polarity. That's why I highlighted the minus sign, because the voltage is going to be inverted. Why? Because the diode is inverted. This canonical cell makes us visualize it, because the switch is usually a transistor, and the driver circuit of the transistor is rather complicated if we want to talk about it in a very small lecture. And the drive circuit is what drives this whole circuit. But for easier understanding, you can think about the switch, because a transistor is on and off, and the frequency of the transistor on and off is what is called the chopping frequency, which is chopping is the DC to DC converter, which drives the circuit. So instead of that, you can think about it as a small switch, manual switch, which on and off, so you can do an easier circuit analysis. Like when this is on, how you can do the circuit analysis, and with this, when this is off, the circuit would be like this. You would remove this. It's easier to understand and to visualize. And in the boost step-up converter, you can see this is the transfer function, and the V output will always be more than the voltage source. A recap, interesting hints: the voltage dividers and voltage regulator are inefficient. I want to show you the voltage divider in Paint. This is the simple voltage divider. I just wanted to give it a hint to you. to refresh your memory about it, this is the voltage DC input, and this is the voltage output. We take just 2 wires from this R node, and you get this function, this transfer function. You can say the output over Vn equals R node over R. And you can change the R node and over R as much as you want. But the problem is you cannot get, sometimes these resistors are too high, very big resistors. They're heavy, they're very, and it's uncontrollable. It's not easy to control. Each time you need a different voltage, you need to change the resistors, which is very inefficient. That's why we call for them as inefficient. And for high efficiency, as we said, we use a high frequency switch as like the transistors and the driver circuit of the transistor, yeah, which controls the whole circuit, you can say. And the energy store buffer, acts like a filter, you can say, which is the capacitor. It stores energy, and the inductor, they store energy, and they filter the output to smooth the sharp edges to make it more DC. As you know, like the Fourier series, from the Fourier series, we define the DC voltage as the frequency 0, and that's what we're trying to get a frequency 0. But using power electronics, it's hard to get only the 0 frequency with no harmonics. You can get some frequencies, but the point is to minimize the other frequencies and to maximize the voltage DC frequency, which is the 0, which is the average value of the curve.